Telescopes have been integral to astronomy ever since Galileo first pointed one at the sky in the year 1609. In this video, I'll describe why we built telescopes, why bigger is better, the two types of optical telescopes, other types of telescopes, why we put telescopes in space, and some techniques such as adaptive optics. Telescopes can see more light than our eyes can simply because they're bigger. We're born with two small lenses in our eyes. If those were bigger, we would be able to collect more light. With a telescope and a camera, we can also take longer exposures than our eyes do. The exposure time of the human eye is around 1/15 of a second. That means every second, your eyes take 15 images back to back. We don't get to adjust that. If you stare at an object, it doesn't get brighter and brighter because we're not taking one long exposure, just a series of short exposures. When I was in grad school, I would take 2-hour-long exposures of nearby galaxies. I could see things that are way too faint to be detected by the naked eye, not just because I was using a 3.5-meter telescope as opposed to my eyes, which have an aperture of less than 1 centimeter, but because the telescope would collect all the light it received from a galaxy over a 2-hour period. Telescopes can also see more detail than our eyes. This is called resolution. It's basically a measure of how close two things can be and be seen as two separate objects. It's like having a screen with giant pixels as opposed to one with tiny pixels. The one with tiny pixels has higher resolution. The larger a telescope is, the higher the resolution. Of course, the price goes up too. A telescope that's twice as big typically costs 10 times as much. The third reason astronomers use telescopes is that they can detect types of light that are not visible to the human eye. With the human eye, we can only see visible or optical light. There are telescopes that can look at gamma rays, ultraviolet, X-rays, infrared, radio, all the types of light. As I had mentioned earlier, a bigger telescope collects more light, and so it can be used to study fainter objects. A bigger telescope will also give you a higher resolution than a smaller telescope. Remember, resolution is how close two things can be and be seen as two separate objects. Here are 3 simulated images of one small region of the sky. The point is not that the images get larger when we use a larger telescope. We can take any image and enlarge it or shrink it. But if we enlarge a low-resolution image, objects in it look even more fuzzy. With a 2.5-meter telescope, we can tell there are a few different objects here, but we can't clearly see what types of objects there are. The pixels are large. 2 objects have to be quite far apart and be seen as 2 separate objects. With an 8-meter telescope, we can tell that the white object is not one single object, but a collection of smaller objects. It could be a cluster of stars or one big galaxy surrounded by companion galaxies. We can see more detail on this image than the other image, and also many more objects. With the 100-meter telescope, we can clearly see that the white object is a star cluster. The yellow object remains mysterious. It could be a galaxy or a star surrounded by gas clouds. We see a lot of stars throughout the image and find detail in the red gas clouds. The first telescopes use lenses to collect light. A lens bends light and brings it to a focus at one point. In fact, each color is focused to a slightly different point, which can make the image appear blurred. I'll come back to that. If you hold the lens close to your eye, you will see things right side up. If you move it away so that your eyes are right at the focal point, you'll just see a blur. When you move it even further back, objects will look upside down. The ray of light that entered the top of the lens ends up at the bottom beyond the focal point, and the ray of light that entered the bottom of the lens ends up at the top beyond the focal point. You can use a second lens to get the rays of light to reconverge or become parallel again. The two lenses together make up a refracting telescope. Refraction means bending. The big lens is called the objective, and the small lens is called the eyepiece. The image will be upside down, but astronomers usually don't care about that. We don't care if the moon or Jupiter looks right side up or upside down. You wouldn't want to use an astronomical telescope for bird watching, though. It'll give you a headache. Galileo used a refracting telescope to make all of his amazing discoveries, including that Venus has phases and Jupiter has moons. Isaac Newton invented the reflecting telescope. Unlike a lens, a curved mirror focuses all the colors to a single point, and so images don't appear blurred. The primary mirror focuses the light to a point inside of the telescope. Newton put a flat mirror that deflected the light off to one side. You can change the magnification of a telescope by changing the eyepiece. So magnification is cheap. What you pay a lot of money for is the objective lens or the primary mirror. If it's larger, you can collect more light, which means you can study fainter objects. And of course, you get higher resolution as well. The world's largest refractor is at Yerkes Observatory in Williams Bay, Wisconsin, a little more than an hour's drive from Harper College. Its objective lens is 40 inches or more than 1 meter across. When it was built in the 1890s, it was the largest telescope in the world. The reason they built such a large refractor instead of a reflector is that they happened to find a couple of 42-inch glass discs that were optically perfect. One of them was ground to make a 40-inch lens. All large optical telescopes today are reflectors. Here are the most common designs for reflecting telescopes. If a telescope is large enough, you can put the camera inside where the focal point is. We call that prime focus. Usually we prefer to deflect the light out of the telescope. If it goes out to one side, that's called a Newtonian. Sometimes it's not the most convenient place to put cameras and spectroscopes. A more common design is to drill a hole in the primary mirror and deflect the light to the back of the telescope. This is called a Cassegrain. There are several optical telescopes around the world that have a primary mirror which is 8 meters in diameter or larger. Here is one of the 4 8-meter mirrors of the European Southern Observatory's Very Large Telescope in Chile. Here is an aerial view of the Very Large Telescope. In a few cases, telescope designers have preferred to build a bunch of small mirrors instead of one giant mirror. The 2 Keck telescopes in Hawaii each have 36 hexagonal mirrors, which effectively make one 10-meter mirror. Here is part of Mauna Kea Observatory on the Big Island of Hawaii, which houses the Keck 1 and Keck 2 telescopes and a half a dozen other telescopes. This image shows Subaru, which is an 8-meter telescope built by a Japanese consortium, the Keck 1 and Keck 2 telescopes, and on the right, NASA's Infrared Telescope facility. Now I would like to take a couple of minutes to describe how telescopes are actually used. Here is Apache Point Observatory in New Mexico. I've spent a lot of time here. The telescope back here is the one I used to get all the data for my dissertation. It's a 3.5-meter telescope, which is not huge, but decent sized. Most large telescopes are built by institutions in 1 or more countries, but they're operated by one astronomer at a time. You can write a proposal saying you want 1 night or 5 nights of telescope time to look at this planet or that galaxy because it will help you answer an important scientific question. If your proposal is approved, the telescope is yours on those nights. I would take a 2-hour-long exposure of one galaxy in one tiny part of the sky, and then another one in another tiny part of the sky, and so on. The next night, whoever was using the telescope might have been looking at Mars. The night after that, someone might have pointed the telescope to a star. What this means is that most of the sky is never looked at by any astronomer. So we're not getting large statistics on different types of objects in the sky, such as stars, asteroids, galaxies. And we're not discovering many new objects. That's why astronomers come together once in a while to build a survey telescope. That's what this is. It's the 2.5-meter Sloan Digital Sky Survey Telescope. It's not all that big, but it did something amazing. It imaged a quarter of the entire sky, one strip at a time. That means it took images of millions of stars, galaxies, and other objects. In fact, it ended up discovering a few hundred asteroids. Stars and galaxies are generally not named after people, but if you discover an asteroid, there's a good chance it'll be named after you. But in this case, these asteroids were discovered by an automated telescope, not by any individual astronomer. So the Sloan Digital Sky Survey collaboration decided that these asteroids would be named after the authors of the first data release paper of the survey. It so happened that I did a few hours of work for that paper, and a nice man included me in the author list. So I have an asteroid named after me. There's an asteroid Morphe floating around somewhere in the asteroid belt. The survey that this telescope was built for was completed by the mid-2000s. The telescope was still working fine, and so it was then used to image the entire Milky Way in great detail. So that was the second survey. When that was done, they came up with a new project. As of now, the telescope has been used to conduct over a half a dozen huge surveys of different parts of the sky to answer thousands of scientific questions. All of the telescopes I've talked about so far look at the same type of light we see with our eyes, namely visible or optical light. Of course, this is just a small portion of the light spectrum. After visible, the best studied portion is radio. Radio telescopes have several advantages over optical telescopes. Number one, they're much cheaper to build, which means we can build very large ones. Radio dishes don't have to be shiny and spotless like optical mirrors. You can use cheaper materials. They can get rained on. You can walk on them and leave your footprints. It won't affect the data at all. If you go out to the very long wavelengths, such as meter waves, the dishes don't even need to be solid. Here is a 45-meter antenna that's part of the giant meter wave radio telescope. You can see another one of the antennas in the back over here. There are actually 50 such antennas in a giant array. You can see here that this antenna is dish-shaped, but it doesn't have one solid surface. That makes it a lot cheaper to build. A second advantage of radio telescopes is that the sky is dark in the radio, even during the day. This means you can operate them 24 hours a day. They can also look through clouds and possibly even through rain. Radio telescopes, if they're just one single dish, do have one major disadvantage, and that is that they do not obtain high-resolution images. The way you get around that is by combining the radio waves from a bunch of dishes, as they do here. I'll say more about that in a minute. For over 50 years, the world's single largest telescope was the Arecibo Observatory in Puerto Rico. This thing is not 8 meters or 10 meters across, it's 300 meters across. Radio telescopes are always reflectors. Light is reflected by the dish onto the receiver up here. In 2016, a larger dish was completed in China. It's called FAST, which stands for 500-meter aperture spherical telescope. As I just mentioned, a single radio dish cannot obtain high-resolution images. We can get around this by linking together a bunch of radio dishes. This is called an interferometer. You capture the radio waves at each dish at the same time and then combine the signal. The first of these was completed in New Mexico around 1970. There are train tracks running next to the dishes. The dishes can be lifted up and placed on a train to move them closer together or further apart. The spacing between two dishes is called a baseline. The longer the baseline, the better the resolution. If you're looking at a bright object and want as much detail as possible, you can move the dishes out and get baselines which are several miles long. If instead you'd like to look at a faint object and want to capture more light with less detail, you can move the dishes close together. When astronomers decided to build this thing, they knew it would be the world's finest radio observatory. The question was, what do we name it? Someone said, it's an array, and it's very large. Let's call it the Very Large Array. A couple decades later, radio astronomers wondered why they should stop there. There's no reason the dishes have to be at the same site. Why not get huge baselines by putting them thousands of miles apart? They built 10 more dishes that are identical to the Very Large Array dishes and placed them throughout the Western Hemisphere, from Hawaii to the Virgin Islands. And they said, what do we call this thing? The baselines are very long. Let's call it the Very Long Baseline Array. Since then, at least half of the world's big telescopes have had large or something else describing how big it is in its name. And it's not just the ones built by the Americans. I've already showed you the largest optical telescope built by the Europeans. It's called the Very Large Telescope. And then there's the Large Binocular Telescope, which is 2 8-meter telescopes in Arizona. And then there's the South African Large Telescope. You've already seen the giant meter-wave radio telescope in India. And of course, China's huge dish tells you exactly how big it is. It's the 500-meter aperture spherical telescope. Here is another interferometer. This is the Atacama Large Millimeter Array in Chile. Here's an image taken by a radio telescope in case you're wondering how they might look. This is Cygnus A, one of the most active galaxies known. If you looked at it with an optical telescope, all you would see is a galaxy in the middle where the red dot is. We wouldn't see these enormous jets shooting out from the center of the galaxy. This is from gas that's traveling at close to the speed of light. The colors are arbitrary. They're chosen for artistic rather than scientific reasons. Telescopes that look at the near-infrared, that is the part of the infrared that's just next to the optical, just past the red, can look through things like dust. If astronomers want to study a dusty cloud, near-infrared is a good wavelength to look at. You can look right through the dust. Likewise, you can look right through a black garbage bag, or for that matter, through clothes. Here is the constellation Orion, seen in visible, X-ray, and infrared wavelengths. In the visible light image, we see mostly empty space and a few stars along with a couple of glowing gas clouds. X-ray, just like the near-infrared, can look right through dust. We can see many more stars in the X-ray image than the optical image because there's a lot of dust in this part of the sky which blocks out light from the stars. In the far infrared, the dust itself starts to glow. The point is that you get a different picture of the universe by using different types of telescopes. All of the telescopes I've talked about so far are on the ground. We also have some space telescopes. The most famous one is Hubble. Here are a couple of other ones. Today there's only one reason to put a telescope in space, and that is to look at one of the types of light that's absorbed by the atmosphere. Notice that I've pretty much only been talking about optical telescopes and radio telescopes so far. These are the only two types of light that make it through the atmosphere all the way down to the ground. So if you want to study gamma rays, or X-rays, or UV, or infrared, you have to go to space. There are a couple of narrow windows in the infrared just past the red that can be studied by NASA's Infrared Telescope facility in Hawaii. which I showed you a picture of. But further out, all the infrared is absorbed in the atmosphere. You could capture some of it from a plane, though. Here is NASA's SOFIA, which stands for Stratospheric Observatory for Infrared Astronomy. Putting a telescope in space is extremely expensive. It typically costs 1,000 times as much as putting the same size telescope on the ground. Let's say you built a $100 million telescope. It would cost $100 billion to put it in space. Putting it on a plane is much cheaper. Here are 3 images from the Spitzer Space Telescope, which captures infrared light. The Flame Nebula is a place where stars are forming. The other 2 are places where a star has died. When a sun dies, it'll turn into something like the Helix Nebula. When a much more massive star dies, it will explode as a supernova, like Cassiopeia A. Again, the colors were chosen just for artistic reasons. This is not how these objects would look to your eye. There used to be a reason to put optical telescopes in space. Turbulence in the atmosphere distorts images and makes them blurry. If you see stars twinkle, what you're actually seeing is the light from the star bounce around in the atmosphere. By putting a telescope in space, we can get 10 times better resolution. Here is an image with the ground-based telescope on the left and an image of the same part of the sky with the Hubble Space Telescope on the right. After Hubble was launched, a technique was developed called adaptive optics, which can remove the distortion caused by the atmosphere. One of the mirrors of the telescope has pistons on the back, which push and pull on it hundreds of times a second, so that each wave of light is caught at just the right time. You can see how deformed the incoming waves are. The telescope mirror itself is deformed to compensate for that, and the light that's reflected off the mirror has nice parallel waves. Adaptive optics is almost as good as going to space for a small fraction of the cost. So there is no longer any reason to launch a general-purpose optical telescope like Hubble into space. We only need to put infrared, gamma ray, X-ray, and UV telescopes into space. If the type of light that we want to look at makes it down to the ground, then we don't need to spend the money to launch that type of telescope into space. Here is an image of Jupiter taken using adaptive optics on the Very Large Telescope. The details you see on the bright and dark bands and on the small storms would not be visible without adaptive optics. The next large space telescope will be the James Webb Space Telescope. This will be an infrared telescope. It could be launched as early as 2021. It will have 18 hexagonal mirrors, which together give it the light collecting area of one 6.5 meter mirror. 6 of those hexagons are shown in this image. 2 other telescopes to look out for in the 2020s are the 30-meter telescope and the 39-meter European Extremely Large Telescope. As I've mentioned, telescopes almost always have something about the size in the name. The Europeans actually wanted to build a 100-meter telescope, which they wanted to call the OWL, which stands for Overwhelmingly Large Telescope. But they figured the Extremely Large Telescope is ambitious enough for now.